I should start mentioning that the work I'm going to report today is in two pieces with different co-authors. So the first piece is with Amit Anaf, Beatrice Signorello and Tobias Wöhrer, and then the second part with Jean Dolbeau and Christian Schmeisser. So here is a short outline of my talk. So somehow, as a long and very simple introduction, I will start with hypocoercive ODEs. And the key idea or the goal is to show how to obtain sharp decay estimates by writing down or constructing appropriate Lyapunov functionals. And then the main essence of the talk are points 2 and 3. I will discuss the Goldstein-Taylor model, which is a two-velocity BGK model, if you like, in two situations, first on the torus and then on the real line. But you should think of this very simple model that I'm discussing here just as one possible application, more to illustrate how to apply this methodology that I'm describing here. So let me start with the simple ODE story. So I'm looking here at this linear ODE with a non-symmetric matrix C. And I call this matrix coercive if it satisfies this inequality for some positive kappa. And let me jump right at one example with this matrix here. So here the symmetric part has this entries 1 and 0, so obviously this matrix is not coercive. Still you have eigenvalues which are 1/2 plus minus this imaginary part, which tells us that all solutions to this simple ODE will decay with an exponential rate 1/2. If you have such a situation with a non-coercive matrix, you will not be able to extract this exponential decay of a solution by a trivial energy method. And with this, I mean, if you multiply your ODE here from the left, just with the transpose of X. And we can see that here in this plot, I plot the norm of the solution X as a function of time, and you see that it goes down in these wiggles. And here at a point like here or here, you have horizontal plateaus, and it's exactly for these plateaus why the energy method doesn't work. Still, if you introduce this modified norm like here, with a matrix P that is adapted for this problem, and here in this example, the matrix P would have the entries 2, 1, 1, 2. Then you see a very nice convex decay, perfect exponential decay like this red curve. And so one natural question is, of course, given such an ODE, how do you find or construct this matrix P, which gives you this modified norm as a Lyapunov functional? So just a little bit more terminology. I call a matrix C hypocoercive in analogy to PDEs if it has a spectral gap. So all eigenvalues should have a strictly positive real part with the spectral gap being mu. So typically for matrices, of course, you would call that positive stable. In such a situation, if we assume that all eigenvalues are non-defective, which means there are no Jordan blocks, then you have this exponential decay of a solution. And the spectral gap constant mu will always be larger or equal to this coercivity constant kappa that we have seen on the previous page. So a simple condition that gives us this hypocoercivity on this ODE or matrix level is if I decompose my matrix C into a skew symmetric part and into a positive semi-definite Hermitian part, then I request that no subspace of the kernel of the Hermitian part should be invariant under the skew symmetric part. So this condition could remind you possibly of the condition of hypoellipticity, for example, in Fokker-Planck equations. So now let me briefly illustrate how to obtain this matrix P that gives us this Lyapunov functional as a modified norm for the problem. And in this context, we have this very simple lemma. So assume that this given matrix C has a spectral gap that I call mu, and I assume that all eigenvalues that have a real part which are exactly equal to this mu are non-defective. So on this spectral gap line, there should be no Jordan blocks associated to that. Then the statement is there exists a symmetric positive definite matrix P such that you have this matrix inequality. And the purpose of this matrix inequality, in order to anticipate a little bit, is that this mu in the end will give you the decay rate. In this case, the sharp decay rate, because this is exactly the spectral gap. If you do have non-trivial Jordan blocks on this vertical spectral gap line in the complex plane, you lose an epsilon of your decay rate. So let me now just briefly show you how to obtain or to construct such a matrix P. Take all eigenvectors of the transpose of your given matrix C and tensor them in this way and sum up all these eigenvectors. Then this matrix P will be the matrix that gives rise to this Lyapunov matrix inequality. I should say from the very beginning that this matrix P is not unique, but no matter which of the possible P's you choose, the decay rate mu that you obtain in your estimate will be independent of that. And what I've shown you here for real matrices works exactly the same way for complex matrices. So just a very simple computation to show you how this matrix inequality can be used. So here is the Lyapunov functional, this modified norm with the matrix P in the middle. If you then differentiate this norm squared, then you get from the OD one matrix C to the right and the transpose of it to the left. And then here in the middle, you see exactly the matrix combination that we have seen on the previous page. So for this combination of matrices, we have the Lyapunov inequality, so we can estimate this by 2 mu times the matrix P itself. So we are back to this modified norm, and we have this exponential decay estimate. So let me mention that strategies like this have already been used for BGK or Fokker-Planck equations. Just a final remark on this ODE level, and I'm coming back to the very same example I've shown on my first page. So here I show you a picture in phase plane in a two-dimensional setting, and here I show you this blue spiral, which is one trajectory of this problem. So of course it spirals into the origin because the problem is asymptotically stable. But I want to point out, whenever this blue spiral crosses the x2 axis, for example here, then this is tangent to this black circle, which is the level curve of the Euclidean norm. So this means exactly at this point, the Euclidean norm of your solution does not strictly decay. This is where you have these plateaus, and same thing down here. So the way out was to introduce such a distorted norm with this matrix P, and the corresponding level curves look like this red ellipse, because then all these spirals will always intersect these new level curves at a non-trivial angle. So in this weighted norm, you will always have a strict decay. So now let me come to the Goldstein-Taylor model and use ideas like those I've shown you before on the ODE level. So here is the Goldstein-Taylor model. We're in 1D, 1x is the spatial variable. I will discuss that in two different settings, first on the torus and later on the whole real line. So we have two species of, say, particles. One, those with the plus that move with velocity 1 to the right, the other one with velocity -1 to the left. And we have a relaxation rate that may or may not be space dependent. So this Goldstein-Taylor model can be seen as a very simple toy model for a BGK equation. As I mentioned before, it's not the model itself that is of our interest here, but it's rather used to apply those tools. Original applications of this Goldstein-Taylor model go back to simple models for turbulent fluid motion, or it can be equivalently written as the telegraphers equation. So in order to analyze that, I first introduce a mass density U, which is just the sum of these two families, F plus and F minus, and the flux density, which is the difference of these two variables. So in these new two variables, U and V, the model can be rewritten like this. And the goal, first on the level, or for the case of the torus, is that for both of these functions, U and V, I want to establish sharp exponential decay rates to the steady state. So the U infinity is the constant, x independent, that is twice the F infinity, which is defined as the average of the two initial conditions. So just take the initial condition for the plus and the minus family and take the spatial average. This is the constant that the mass density will converge to, and the flux density will converge to 0. First, I will discuss that for constant sigma, which is the easy case, the very well-known case, and then I want to use these ideas for x-dependent relaxation rates. So in the case on the torus with the constant relaxation rate sigma, I Fourier transform the equation or the system for U and V from the previous page. So I have this 2x2 ODE for each spatial mode with the index k, with the integer index k. And this matrix that appears here is what I call the matrix CK. So first, if we sort out the 0 mode, so here these elements are then 0, so we see that the U and the V for the 0 mode are decoupled. You have immediately their solution. So let's go to the other modes. Here, let us first look at the eigenvalues of this matrix CK. So when the index k is small, you have two real eigenvalues like this solid dot and this dot here. And then when the modal index k becomes large, you have complex conjugate eigenvalue pairs like these two yellow dots. So they are here on this vertical line. So let me distinguish between three cases now, depending on the modal number. For the low modes, as I said, we have two real eigenvalues. And what is more important for the exponential decay is the small one. So what I call the lambda minus, that's this solid dot, because this will determine the final global exponential decay rate. And for this ODE here in this first line, we can construct this scaling matrix, what I called before the matrix P. It depends on the index K, of course. And if you compute it in this example, this is what you get. And this matrix P is a function of the modal number K. I now want to interpret this matrix family with the index k in the physical space. Then this can be seen as this differential operator, or the matrix with these differential operators here in the off-diagonal terms. Then we have a case 2, which may or may not be present. So when the modal number k is equal to the decay rate sigma over 2. So this would be an eigenvalue, a double eigenvalue here at the intersection of this vertical line here at around 2.5. In this case, the ODE is defective, so the corresponding decay would be an exponential factor plus multiplied with this linear term here. I will skip the defective case, just assuming that the sigma over 2 is not an integer, just to avoid technicalities. Then we have the third case. In the third case, this is for the large modes. We have complex conjugate eigenvalue pairs. Their real part is always sigma over 2, and the corresponding scaling matrices look like this. So again, I want to consider them as a family of matrices with this modal index k. Now, when I consider this matrix family in physical space, they become a family of pseudo-differential operators with this inverse derivative operator here in the off-diagonal term. So with this preparation, we can now, from a global point of view for the PDE, distinguish three situations. In situation A, when sigma, the relaxation rate, is smaller than 2. In this case, all the modes are in the last case. So let me briefly flash back. So in this situation A, all eigenvalues are this complex conjugate pairs. They are on this vertical line. So they all have the same real part sigma over 2. This means if I want to construct a Lyapunov functional for this example based on the modal information, I call this E for my Fourier transform variables U hat and V hat. I just add up all the modal contributions of these modes or of these norms with the modified norm P depending on K. So since this matrix, the last matrix PK, briefly flashback, can be interpreted in physical space as this pseudo-differential operator, I can write down this Lyapunov functional as this pseudo-differential, or here the L2 norms of the two components, and then for the mixed term I get this antiderivative on the variable u. I put a tilde here because I subtract, for technical reasons, the average of this variable u of the mass density, which is preserved in time. The situation B is when sigma is equal to 2. This is defective, and here for the purpose of this talk I will skip that. Then we have the relevant situation C, where the relaxation rate is larger than 2. In this case, we have a mixed situation. The low modes are in the first case from the previous slide, so they correspond to real eigenvalues, and they will only determine the global decay rate. And the high modes are in case 3. They are these complex conjugate eigenvalue pairs. So if we again think back to the same strategy that we have done here, we would get two different symbol matrices, symbol for a pseudo-differential operator, for the low and the high modes. So if you want to translate that back to physical space, we would have a pseudo-differential operator with a non-smooth symbol, which would be very unpractical to do computations on. So there is a remedy for this situation where we have these mixed modes. So first of all, let us observe that is only the lowest mode, when k is equal to plus minus 1, which actually determines the global decay rate. This is the spectral gap of the PDE that is inherited from the modal discussion. So that tells us that, in fact, although we have computed the decay rates for the higher modes, they are faster than the global decay rate. So there's some margin where we can give up the sharpness in order to adjust the decay rates. So this means for the higher modes, it is fine to use suboptimal modal norms because their decay rate is in some sense too high anyhow. It doesn't matter if we lose a little bit there. So for modes with index 2 and higher, we will construct now or invent a different norm, not the one that we have derived systematically before, in order to be able to combine this setting of treating the lower and the higher modes separately. So here in this small lemma for this situation sigma larger than 2, I just cook up a new matrix pk. It looks similar to what I've shown you before, but in fact it is different. It is different for all k. And again, this matrix family can be interpreted as a pseudo-differential operator in this form. And the essential feature is, on the matrix level, it satisfies this Lyapunov matrix inequality for all modes k. The important aspect is here, this family of Lyapunov matrix inequalities is uniform with respect to this mu, which is the sharp global decay rate. And the advantage over what we have derived before is, here I have one shape of a matrix pk that can be easily translated in just one pseudo-differential operator that will take care of all the modes. So in other words, this family pk that I've just found here is good enough for the optimal decay, in the sense that this matrix that I just cooked up is for the lowest mode the same one as the one that I derived for the lowest mode. This is important because this is the only mode that counts. For the other modes, it's different, but it gives you the same decay rate. And as I just mentioned, this matrix family gives rise to this simple pseudo-differential operator. So with this information, I can now use this matrix pk as a Fourier symbol, and the corresponding Lyapunov functional is of this form. So first there are two norms of the two components of the solution, and then for the mixed term, we have this antiderivative. And the result that one can find with this Lyapunov functional is, for small relaxation rate sigma, you have exponential decay of this Lyapunov functional with the sharp rate sigma. For the case where you have a large sigma, large relaxation rate, you can use the same Lyapunov functional. Just observe that the index up here was sigma, and now it is 4 over sigma. So you just have to adapt the mixed term, the strength of the mixed term. And again, you recover the sharp decay rate in this case. Now, if you wish to go back to an L2 estimate, you observe that this Lyapunov functional up here is equivalent to L2 norms. And at this point, let me mention that these sharp rates and essentially also these Lyapunov functionals could also be recovered from this paper from Dolbeau, Moore, and Schmeisser from 2015 if one optimizes a tuning parameter there on a modal level, a tuning parameter that is included in their functional. So what I want to do, the last step, is from these decay estimates on the Lyapunov functional, I want to go back to L2. So here I show you the L2 decay estimates with the sharp rate. So here's the final result, which is in this joint work with Anaf, Signorello, and Wöhrer. Here, this mu of sigma is the sharp exponential decay rate, and here are explicit multiplicative constants for this optimal decay rates. Just a phenomenological interpretation of what is happening here. In this plot at the bottom, I show you this decay rate. Here, this reads mu of sigma as a function of sigma, as a function of the relaxation rate. So what happens in this Goldstein-Taylor model is, first, if you increase the relaxation rate, the decay will increase linearly up to this point here, which is the point where you have defectiveness in the ODE. And then the exponential decay rate will reduce again. And phenomenologically, the reason for that is you have larger and larger relaxation. So naively, one could think the convergence to equilibrium will also increase. But you switch so quickly between these two families with the two velocities that you don't let enough time that you also have transport in the x direction. And therefore, the equilibration in x happens slower and slower. So now let me briefly show you the interesting extension when the relaxation constant is x-dependent. So the unpleasant situation is, of course, a modal decomposition doesn't work there anymore when you have space-dependent coefficients, but still the Lyapunov functional that I've shown you before with this antiderivative can still be used. I will not show you the estimates because they are rather technical, but here's the result. So with this same Lyapunov functional, you can get an explicit decay rate. The index has to be chosen here in relation to the lower and the upper bound for your relaxation rate. And you also find an explicit exponential decay rate. So when doing so, there are pros and cons. So first of all, this strategy that I just sketched here can also be applied to BGK models with more than two velocities. And in this paper that I mentioned before, we have done it for 3 velocities, for example. There's a negative aspect. This constant alpha star for x-dependent relaxation rates is not optimal. So a brief review to the literature. For 2 velocities, the sharp decay rate for the case where sigma is x-dependent is included, or is the essential message of this paper by Bernard and Salvarani. But since this paper is based on the equivalence to the telegrapher's equation, there's no chance to extend their strategy beyond 2 velocities. So now let me briefly, towards the end of my talk, give you a hint how to extend the whole story from the torus to the real line. And here, for the moment, I will only talk about a constant relaxation rate 1. So here's again the Goldstein-Taylor equation. Now on the real line, I introduce U as the mass density and V as the flux density, and I Fourier transform the system. It looks like in the torus case. The only difference is the modal number psi is now a real index. So compared to the torus case, there are now 3 problems that we should consider. First of all, let me look at this plot here. So let's first look at the orange curve. The orange curve is the decay rate, I call it mu, as a function of the modal index psi. So first of all, we see that the decay rate, the modal decay rate, will vanish when psi becomes closer to 0. So there is no uniform lower bound for the modal decay rates, which tells us immediately it is completely hopeless to dream of an exponential L2 decay in this problem on the real line. The only thing what we will get therefore is an algebraic decay. Second problem that we have to consider. You see that this orange curve has two distinctly different branches. The first curve, which looks like a parabola, and then this constant. So this is a little bit like the situation C on the torus, where we also had this mixed case between the low and the high modes. And there we also had to think of how to cook up a matrix P, this scaling matrix on the modal level, in order to be able to treat both cases simultaneously. So the problem that we have already seen on the torus there would be if we would use the sharp decay function, this orange function, we would get a pseudo-differential operator with a non-smooth symbol. Third problem that is present here. In the torus case, I avoided, for the purpose of the talk, the defective situation. So that's when psi is equal to sigma of the 2 over 2, by just saying sigma over 2 is not an integer, I don't consider these problems. And then I could just skip that. On the real line, this defective situation, this point, cannot be skipped. It will always be there. And if you look at the level of estimates, of the modal estimates, several constants will blow up, because in that case, you simply don't have an exponential decay. So therefore, one possible remedy that I'm going to show you today to solve all these three problems is to somehow give up a little bit on the best possible decay estimate here in this intermediate region here, and approximate this orange curve by this dashed blue curve. So you see here close to 0, this is a really good approximation, and then for large psi it converges to this constant. So how can you do this approximation? Well, first you again have to approximate the scaling matrices, and this is cooked up. There's no systematic way to derive that. There you have to play a bit. And in fact, this matrix family, now as a function of the modal variable psi, turns out to be a really good approximation of the sharp, the optimal scaling matrices in both limiting regimes, for small modes and for the large modes. Then from this cooked up scaling matrix, you can compute the corresponding spectral gap for the modal ODEs. And this is the function that you get. So this function, of course, doesn't tell us much. If we look back, this is exactly this blue curve. And we see that this is a reasonable approximation, at least in the limiting regimes, for the perfect decay function. And it avoids the defective case, the technical one, because we have given up a little bit on picking out or following the sharp decay rate. So having this approximation, one can again write down a global Lyapunov functional just by integrating up all the modal norms with this scaling function p tilde of psi that you see on the first line. And since this is a rational function of the modal variable psi, this can be translated into physical space with a slightly more complicated pseudo-differential operator that appears here, but at least it has a smooth symbol. So there is hope to be able to do computations with such a Lyapunov functional. Actually, in the proof that I'm going to show you on my next and in fact last slide, we used the L2 decay on the modal level. So here the approximated decay function, and here the multiplicative constant, which comes about, so this is the numerical condition number of this matrix P, and this comes about by going back and forth between the P norm and the Euclidean norm. So here is the final result that we obtained with Jean, Christian Schmeisser, and Tobias Wöhrer. So in L2, our solution with the components U for the mass density and V for the flux density. So this decays as a function of time. And on the right-hand side, we have this nasty term. So before going a bit and explaining a bit what we see here on the right-hand side, let me briefly mention what has to be done here. You have to split the treatment in the estimates between the high and the low modes. Say high modes larger than some constant R. For the high modes, you still have exponential decay in L2 because those modes have a decay rate that is uniformly bounded. This is what we see here in this last term. So this is bounded by the initial, by the L2 norm of the initial data, and here a uniform exponential decay rate. For the low modes, however, where you don't have a uniform lower bound, we invoke here the L infinity norm of the Fourier transform solution in order to be able to estimate that. And then one is able to extract at least algebraic decay. And this is what we see here in this first term. So this corresponds to the L infinity norm here. And here's the algebraic decay rate. In the end, you also see an infimum over this truncation parameter R, so you can optimize with respect to R. So let me conclude. In my talk, I've started with modal ODEs, and I've shown you how we can derive sharp exponential decay rates. And then I have applied that to a simple PDE model. First, I've shown you how these scaling matrices can give you a hint how a pseudo-differential Lyapunov functional can be constructed, with the goal to be able to treat also PDEs with non-constant coefficients. And then for the hypocoercivity on the whole real line, I explained this splitting between the low and the high modes, leading in the end to an algebraic decay rate. So the story with the pseudo-differential Lyapunov functional is included in this paper here, and the story with the hypercoercivity on the whole real line is included among many other aspects in this long second paper here. I think time is long up, so thanks for being patient and thanks for your attention.
Thank you very much. Are there any questions? May I ask one short question? Let's stay with the finite ODE system. It seems that you have a very rigid structure. And a natural question is, how much can you perturb it by something nonlinear? So do you have an idea of what would be the obstructions if you put a nonlinear perturbation to this linear ODE system, which of course has the right behavior at the origin, the right behavior at infinity, and is of course sufficiently small?
Yes. Yes and no. Not on the level of the nonlinear ODEs. This is in one of the programs of the things to do next. But my yes part concerns nonlinear BGK equations that we studied with Eric Hallen and Franz Achleitner. So the way we dealt with nonlinearities there was to linearize the PDE around the steady state, and then to treat the linearized problem with the strategy that I've discussed here. And then in the final step, taking into account the nonlinear perturbations and show, at least locally around the steady state, that they are smaller than what can be controlled by your exponential decay rate. So this was the first examples where we were able to deal with nonlinearities in a local way. But what you mentioned to include the nonlinearity in the ODEs is one thing that we want to discuss or analyze next.